Thanks everyone for coming. Today I'm gonna give you a talk, try to compare the effect of elevated CO2 on the genotype with different aluminum tolerance in acid soil. As we all know, the atmospheric CO2 concentration has increased continuously due to human activity. It causes a lot of problems like the global warming and the ocean water acidification. Like in Australia, we lost a lot of reef. So now I invite and welcome all of you to come to Australia to visit the Great Barrier Reef. And the Nemo told me it's amazing. And fortunately, elevated CO2 increase the photosynthesis and increase the plant productivity and finally increase the grain yield. But another problem the plant faces with is acid soil. It accounts for around 40% of the world arable land, and it continuously increasing because of the fertilizer import and agricultural harvest. We know that acid soil can reduce the plant productivity and the yield due to the low concentration of nutrients like P, and also it has a very higher concentration of toxic metal, mainly aluminum. Aluminum can replace the bonding site of magnesium and calcium, and it also can cause form irreversible string structure with the protein, which will finally denature the activity of protein. So as a result, the aluminum will inhibit the root elongation, and it causes the root swelling and root ruptures. The question now is, what will happen if we grow the plant in acid soil on the elevated CO2? We think maybe elevated CO2 can enhance the plant ability to counteract aluminum toxicity. We mainly focus on the bread wheat. For wheat, the main way to detoxify aluminum is to have organic acid efflux. The main way is the Malate efflux, which is confirmed by TLMT1 gene. This gene is induced by aluminum, which is the main way to detoxify aluminum. For another organic acid, which is citrate, it is confirmed by TMAT1B gene. This gene is constitutively induced, but it's less effective. We hypothesize that elevated CO2 maybe can increase the organic anion efflux, which will improve the aluminum resistance and the root growth, which finally will increase the grain yield of bread wheat. So we did a phase experiment in the field to test this hypothesis. We want to know the growth and the yield response of wheat lines differing aluminum resistance to elevated CO2 in acid soil. We use 2 layers of the soil. The top layer is less toxic than the subsoil. It is a randomized split plot design. We have 2 CO2 concentration, 6 wheat lines, and 4 replicate. The main plot is the CO2 concentration, which is 400 and 550. And the subplot is 6 wheat lines differing organic acid efflux. Actually, we have 3 near isogenic pairs. The first, which are E8, E8, E-grade, E-grade, TMAT1B, EGA-Berg, TMAT1B. Compared with E8, E8 has higher Malate efflux, and E-grade TMAT1B has higher citrate efflux compared to E-grade. And EGA-Berg TMAT1B has higher citrate efflux compared with EGA-Berg as well. But both genotypes has higher Malate efflux. So when you look at this figure, you will think about, okay, we won't grow any sensitive genotype like E8 and E-grade in the field in the future. But what's next? It is, I think, for the lines with citrate efflux, which is egret TM-1b, and EGA-Burke TM-1b, that has a lower yield response compared with the lines with only malate efflux. So what happens with these lines with citrate efflux? We notice that for all the genotypes, almost all the genotypes, FSCO2 can increase the total plant productivity, but not for the ET8. So it indicates that FSCO2 can promote the biomass allocation to the grain. More specifically, when we look at the harvest index and the root shoot biomass ratio, we find that for the genotype with only malate efflux, which is ET8 and EGA-Burke, FSCO2 will increase the harvest index, and it also decreases the root biomass allocation to the root biomass allocation, which possibly save this carbon to the grain. So what happened with the lines with citrate efflux? Why for lines with citrate efflux it can't promote the biomass allocation to the grains? We find that actually for lines with citrate efflux in the vegetative growth stage, FSCO2 increases its tiller formation, and it remains stable at the maturity stage. But unfortunately, FSCO2 didn't increase the effective tiller, which is the air, for the lines with citrate efflux. And also we notice that FSCO2 can increase the total root biomass of the lines with citrate efflux. And when you look at the root length, you find that FSCO2 has no impact on the fine root length of the lines with citrate efflux, but it increases the coarse root length of the line with citrate efflux. We did a hydroponic experiment, try to confirm our field experiment. We found that we measure the longest root length, and we found that for the lines with citrate efflux, FSCO2 do increase the longest root growth, which means FSCO2 can promote the biomass to the primary roots or the nodule or primary roots here to explore the deep soil. So we have this kind of basic framework that for the lines with citrate efflux in the vegetative growth stage, FSCO2 will promote its biomass allocation to the coarse roots and to form a tiller as well. But this continuously biomass allocation to the roots finally will limit its biomass allocated to grain, and thus to reduce the effective formation and yield increase compared with the lines with only malate efflux. So we also want to understand how FSCO2 increase the coarse root growth, mainly like the primary and the nodal roots. We found that FSCO2 has no impact on the malate efflux and also on the aluminum accumulation in the root tips, which means FSCO2 has no impact on the aluminum resistance of the root tips. But FSCO2 do increase the citrate efflux. So we think that for the lines with citrate efflux, FSCO2 may promote its citrate efflux to promote its primary root growth with some unknown reason. And also we want to know why FSCO2 promotes the deep root growth. From this figure, we find that FSCO2 actually decreases the water consuming per plant per column, which means for the plant growing on FSCO2, it consumes less water. So it's less likely induced by the water deficiency. So with summary, FSCO2 can increase the grain yield of aluminum-resistant lines in acid soil, and the citrate efflux could promote the increased biomass allocation to the coarse root elongation without elevating aluminum resistance of the root tips. So I would like to thank to our plant and soil interaction group, and thanks to my supervisor, Professor Tong here, and James Hunt here, and thanks for Dominic Larisella, Clayton Butler, and James Orisula for soil collection. Thanks to the funding for phase study from the GRDC and the Australia government of Department of Agriculture and Water Resources. And also thanks to the overseas PhD scholarship from Australia government. That's it. Thanks for listening.